Okay, guys, welcome to the final part of lecture 4. So we get back to example 4.1, where we had already the expression for lambda, okay, for lambda, and the expression for lambda here, okay. So lambda is a function of I and x, and we will solve for I. So I will be the function of the lambda and x, and therefore we can plug I in this expression to calculate the Wm, okay. And after you have the expression of Wm, you can now apply the formula we just developed to calculate the force created in that structure, okay, by electric origin. So this is the force created by electrical energy, and that's why we have the small e here, okay. We have the small e here to remind you it's from electrical, and then you can plug the expression for lambda, and you have the final expression down there, okay. uh, but that is a very special case where you can easily get the current as a function of two variables lambda and x. In general case, okay, we normally have the lambda as a function of I and x, and it may be difficult to solve for current as a function of lambda and x, and therefore it would be more helpful, would be more convenient if we can compute the force directly from the lambda as a function of I and x here, okay. So let's see how we do that. So first we calculate the dWm, which is this, and we try calculate this one, okay. We try this one, and we see that this d lambda I will be I d lambda plus lambda di. So we see the two component here, okay. We see I d lambda here and there, and therefore I d lambda would be d of lambda I minus lambda di. So we plug this one into this, okay, and we get this. And now we combine these, okay. We combine these two, okay. So we will put the we will bring these two, okay. We'll bring these two to the left hand side, okay, and we'll bring the Wm to the right hand side, and then turn it, and then switch side. So we get d of lambda I minus Wm will be lambda di plus f dx, okay. Now we call this function, we call this lambda I minus Wm is Wm dash, okay. Obviously Wm dash is a function of I and x. And now what if we calculate dWm dash? What if we calculate this one, okay? Mathematically it would be partial differentiation of Wm dash with respect to di with respect to the current and di plus partial differentiation of Wm dash with respect to x multiplied by dx. And similarly to the previous one, so remember we have this as well, okay. So that d of Wm dash will be lambda di plus f e dx, okay. This is equal to f e dx plus lambda di, okay. Sorry for the handwriting, but I guess you see what I mean, okay. So this is fe, okay, and this is lambda, okay. The final problem we might have here is how to calculate this one, okay. We apply a similar method like we do for Wm, and we can finally prove that we can do this directly from lambda as a function of I and x. So here, if you have a magnetic structure and we can find out the function lambda as the function of the two variable of I and x, then we can go ahead and calculate the Wm dash Ix like this, and then apply this formula, okay, to calculate the force. So this is the example for you to see how we do that. So here we have this one is not moving. This one is attaching to something, and it stay there. It's got a coil on it, and this one can move to the left or to the right, okay. And it has a damper here and a spring here, so it can move left or right, okay. So we apply we will build the magnetic equivalent circuit, and then we calculate the flux first, okay. After that, we can find out we only have one coil, remember, so we only have one flux linkage. After this, we'll go straight, okay, and calculate the Wm dash here, and then apply this formula, okay. Remember, no minus here. If you calculate it with Fe with Wm, then it will be minus partial differentiation of Wm with respect to x. But here, the force is calculated with the partial differentiation of Wm dash with respect to x, no minus here. However, you will see that the result will be a negative one, okay. You see that this is positive, this is positive, 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 and positive here. So the final product here will be negative. What does that mean? Okay, go back here. We see that this is the positive direction of x. X is the distance between this not moving part, okay, the fixed part to the moving part here, okay. It's basically that. And when you have a negative force, it means the real direction of the force on this component will be like this. It's in the opposite direction of this direction, okay. We can find out the direction of the force acting on a structure very quickly using some common sense. I'll tell you in the live stream, okay. So graphical interpretation of energy and core energy, they are two parts, okay, on the lambda x plane, lambda I plane, sorry, on the lambda I planes. And the core energy calculation of force for two electrical and one mechanical port system. But this is an example when you have more ports. So on electrical side, you have two ports. So you have energy and power from port 1 and port 2. So V1 I1 and V2 I2. You also got some energy out of the mechanical port. So with this one, okay. Similarly, we can define the energy, store energy function Wm here, which is the function of lambda 1, lambda 2, and x, okay. However, we know that it's going to get really difficult, really hard to calculate it, so we'll go straight and define, okay, lambda 1 I1 plus lambda 2 I2 minus that Wm will be our Wm dash here, okay. And therefore we can prove that the dWm dash will be lambda 1 di1 lambda 2 plus lambda 2 di2 plus Fe dx, and therefore this Wm dash will be the function of I1 and I2 and x. And here it's get a little tricky. When you go calculate the Wm dash here, remember that we need to find special path. In this case, you can see that we go along the y the I1 axis, okay, where I2 is 0, and then we calculate one component. And when the first current is at the final value, okay, at the final value I1, it went from 0 to 1, okay, and finished at 1. So now we fix the current I1 and we calculate along the I2 axis, and we will get the second component, okay, of Wm dash. We can generalize this. So here we will see that it's very abstract here. We have N electrical port and M mechanical port. So we can build the Wm dash like this, okay, like this, which is which will have N component from lambda I di I from 1 to N, and also M component from Fe I running from 1 to M, Fe dx, Fe I and dxi, okay. And then we will have N equation, okay, to calculate lambda, and we will have M equation or formula to calculate Fe, okay, from Fe1 to Fem. It's very abstract. You don't have to take this, okay, but we want to introduce how we generalize this, okay. And in that zero case, you want to calculate Wm dash. You will go on the I1 axis first, and then I2 axis, and so on until you come to the In axis. So you do N components for the Wm dash, and then finally you can calculate, okay, the force and the torque with the equation or the formula we gave you in the previous slide, okay. So this is in the last slide. Here we have an example, so you see how we apply it. So to make it short, we give you the function lambda 1 as a function of I1, I2 and I3, okay. Lambda 2 is a function of I1, I2 and I3, okay. And lambda 3 also the function of those three current, okay. We have here two mechanical angle, phi and C, okay. So we calculate Wm dash by going through I1 axis first. I2 and I3 are 0, okay. And then we go along the I2 axis. Remember, I1 is at the final value, I3 is still 0, okay, and I2 is moving, and the final component will go through I3 axis where I1 and I2 at the final value, and I3 is moving, okay. So we can get this expression. And to calculate the torque, remember we have rotational angle, so we will calculate the torque. So the first torque component will be calculated as the partial differential of Wm dash with respect to phi. So that theta Te phi, okay, and this is Te on C axis. So we calculate it with this second formula, and you will use this expression to calculate, but basically you only need to care about these two components. Those are independent of any angle, so when you calculate the differentiation, it will be 0. They will give you 0 answer, okay. So that's the end of our lecture.